Hello and welcome back to my YouTube channel. In this video, we will take a look at phase portraits of dynamical systems. Previously, we were able to solve for our eigenvalues and eigenvectors. We weren't able to conclude on the behavior of the system, whether it was stable or unstable node. Now, if we recall, we had lambda 1 to be equal to 4 and lambda 2 to be equal to 2. Now, when we see lambda 1 is greater than 0, lambda 2 is also greater than 0. Since lambda 1 and lambda 2 are both non-zero or are both positive, then the system is an unstable node. Now, the system is an unstable node because lambda 1 and lambda 2 are positive. If lambda 1 and lambda 2 are both negative, we have a stable node. So that's the conclusion of the system that we had previously solved. Today, we will take a look at phase portraits. Phase portraits are visual representation of the solution of a dynamical system. It means when you are able to solve for the eigenvalues and the eigenvectors of the system, how you represent them visually is called a phase portrait. This phase portrait allows us to view the solution curves in the phase space. The directions of the system are generally depicted by the eigenvectors. So it means the direction system is determined by the eigenvectors. And the direction of the eigenvectors are also determined by the eigenvalues. When the eigenvalues are different, we will have different directions for our eigenvectors. So we will take a look at the types of phase portraits. So the types of phase portraits. Now, the first type that we are going to look at is the stable node. For this type, if this is our coordinate system, we have our x-axis and y-axis. Now, there are two phase portraits for the stable node. So we will draw the other adjacent to it. So remember, these are y and these are x. Now, the phase stable node we will look at is when lambda, we have two eigenvalues, lambda and mu, and lambda is less than mu, which is less than 0. And when lambda is equal to mu, and they are both less than 0. If lambda is equal to mu, which is less than 0, it means they are all negative. So for stable node, it means the eigenvalues are negative. Is that okay? So if our eigenvalues are less than 0, our solution curve will be given by x of t is equal to this is how the solution of our system is given by. So if we want to plot this solution on this phase portrait for lambda is equal to mu to be less than 0, we see that our solution will cross at a 45-degree angle up for t greater than 0, and our solution will cross the 45-degree downwards for t less than 0. Is that okay? So t going to negative infinity and t going to positive infinity. So in what we are saying is this for all t belonging to the real numbers. Is that okay? So for this case, if it is stable, all the directions will point toward the origin. So our solution curve will move toward the origin. And we see that this is our phase line. Where I'm using the red ink is called phase line. We call them phase line because those are what represent our eigenvectors. Now remember, we are choosing a generic system. For generic systems, we will have P, which is our invertible matrix, which we got from our eigenvectors to be 1, 0, 0, 1. So they will lie on the x and y axis. These phase lines are the ones in red. Since we are picking a generic system for this stable node, this is also going to be the phase line where this is pointing. So our red lines represent our phase lines. They are the ones which will help us to plot our solution curve on the phase space. If lambda is the eigenvalue that gave us this eigenvector, and mu is the eigenvalue that gave us this eigenvector, it implies our mu phase line for mu will be here, and our phase line for lambda will be here. Now, mu is greater than lambda, so the solution curve coming from infinity will be parallel to mu, and as it approaches 0, it will be the phase line of mu as the solution increases or decreases. In this case, the solution curve is decreasing toward the origin. Solution curves come this way, and as it's getting closer to the origin, it will bend. Now, as it bends, it comes like this. Okay, they're all tending toward the origin. Sorry for the way my solution curve is looking. Please bear with me. So we have different solution curves coming from infinity. They are parallel, and as they reach 0, they tend to bend. Is that okay? And they pass through the origin, then they continue down. Now remember, they're all going toward the origin, and your phase lines are telling you the direction in which your solution curve will be. So our solution curve will have this direction, will have this direction, this will have this direction, and this will have this direction. This is for t. This solution curve that I have drawn is for t greater than 0. Okay, so it belongs to R plus. It's the positive part of the real line. And for t less than 0, which is t going to negative infinity, our solution curve will come this way. And this way. Okay. Solution curve will come this way. Parallel, then bend toward the origin, was stable, parallel to mu, then bend toward the origin. So our solution curve will come this way. Is okay? They're all going toward the origin. The one I just drew belongs to a negative part of the real line. Okay. I think the first one should be less than, greater than or equal to 0. This one should be less than 0. Okay, so that's it for the stable node. We will consider the unstable nodes next. So 2. Now, for the unstable node, remember we are still using the generic phase portrait. So we'll have eigenvectors to be on the coordinate axis. So we have our system to be in this form, system to be in this form. There's our y-axis, there's our x-axis, y-axis, and x-axis. Now remember, for unstable node, we have our lambda to be greater than mu or less than mu, and they are both greater than 0. Or we have 0, which is less than lambda, and lambda is equal to mu. So we will use the first phase portrait E as phase portrait where lambda now we'll use our phase portrait E as a phase portrait where lambda is greater than 0 and less than mu. We will use our second phase portrait to plot where lambda is greater than 0 and equal to mu. Our phase lines are pointing outward from the origin. So our phase lines are like this. Phase lines are like this. So our system will be in this form from 45-degree angle up, 40 greater than 0. And 40 less than 0. Our phase lines will give us the direction. So we'll have our direction pointing this way, this way, this way, and this way. Now, our mu will be here, and our lambda will be here. Our solution will start this way, and as it approaches infinity, will parallel to mu. Solution will start this way, and as it approaches infinity, will be parallel to mu. Our solution will start this way. As it approaches infinity, it will be parallel to mu. Solution will start this way. As it approaches infinity, will be parallel to mu. The same would happen for the opposite side. So we'll have something like this. Like this. And again like this. And like this. So we'll have a direction to be in this form, in this form, in this form, in this form. Some of you might be thinking that this is the same as the one I drew up. Yes, it's because of where I placed my mu and my lambda. If this is my coordinate plane, if this is my plane, we have our y and we have our x, and mu is this and lambda is this. And for mu greater than lambda, wherever mu is, the solution curve will be parallel to it. That's what you have to remember. And these are the phase lines. Let me draw the phase lines first. So the phase lines are like this. You always point outward for the unstable. And our solution curve will be parallel to mu. So the solution curve will start like this and be parallel to mu. Start like this, be parallel to mu. Start like this, be parallel to mu. Start like this, be parallel to mu as it approaches infinity. Start like this, be parallel to mu. Like this, be parallel to mu. Start like this, be parallel to mu. Like this, be parallel to mu. It's for all time. So a solution curve will be like this. What you have to keep in mind is the value of mu and the value of lambda. If you have lambda to be 2 and mu to be 4, our solution curve will be like this. And if we have the same, which we then reverse, if we have, excuse me, if we have lambda greater than mu, and we have lambda to be here and mu to be here, you will see that in this case, lambda can either be 4 and mu can be 2. That will give us this case. Is that okay? So in this case, lambda is less than mu, and in this case, mu is less than lambda. Now you're going to the next one. The next one is you have a focus. So you have a stable focus. You have a stable focus. We have two diagrams for it. We use two diagrams to represent them. Now these two diagrams represent when B is greater than 0 and when B is less than 0. Now, for stable focus, we have our eigenvalue lambda to be equal to A plus or minus IB, where I is the imaginary number. And in this case, we take B to be greater than 0. That means we are taking lambda to be equal to A plus IB here. And here we're taking lambda to be equal to A minus IB here. Generally, we take A plus IB. We always take B to be positive. We rarely take B to be negative. So be mindful of that. For the stable focus, we have a complex number. And for this complex number, the stability is determined by the value of A. So A has to belong to a negative real space for both of them. And B has to be greater than 0 for this, and B has to be less than 0 for this. If A is negative, we have a stable focus. If A is positive, we have an unstable focus. And this is how a stable focus looks like. We spiral toward the origin in an anti-clockwise manner. So we spiral toward the origin in the clockwise manner. We spiral toward the origin in a clockwise manner for B less than 0. So we have a direction, we have a direction, we have a direction, we have a direction. So this is for when B is greater than 0. So we have our lambda to be equal to A. Remember, A belongs to a negative dual space. A plus IB. And for this, we have our lambda to be equal to A minus IB. Generally, we use A plus IB always when you're about to find your eigenvectors, or when you're going to find your eigenvectors, we always use A plus IB. Remember, A is a negative value in this case. Next on our list, we have unstable focus. And unstable focus, we still have our complex number, A plus or minus IB. But in this case, A belongs to the positive real part. So when we have our coordinate plane, our X and Y plane, our Y next, we'll have this for B greater than 0, and this for B less than 0. For B greater than 0, our system will spiral outward in an anti-clockwise manner. Start from the origin, and we go out. Is that okay? For B greater than 0, we spiral anti-clockwise. So this is how we move. We're given that direction. For B less than 0, we'll spiral clockwise out of the origin. So clockwise out of the origin. We give it our direction. So these are the different types of phase portrait for stable node, unstable node, stable focus, unstable focus. Next, we will take a look at saddle. Now, a saddle is quite unique. It's quite unique because it has eigenvalues which are both positive and negative. Since you're dealing with two eigenvalues, one will be greater than 0 and one will be less than 0. So whenever you have eigenvalues, opposing eigenvalues, which is one positive and one negative, you have a saddle. If this is our y and this is our x axis, remember we are using the generic system, so we are using p to be 1 0 0 1. Lambda will get us 1 0, mu will get us 0 1. Now in this case, our phase lines will lie on the x and y axis. So we have this to be mu and this to be lambda. Now, lambda is greater than 0, so it's unstable. Mu is less than 0, so it's stable. So mu is on the y-axis. If it's stable, this will be the direction. Okay, I think I should use a different color for easy identification of our phase lines. Is that okay? Lambda is greater than 0, which is what? Unstable. So if you have eigenvalues which are positive, you always have outgoing directions. And if you have eigenvalues which are negative, they have incoming directions. So these are our phase lines are going to be like. And we are going to follow our phase lines to draw our solution curves. So we start from the top. Remember, we are following our phase lines to draw our solution curves. Start from the bottom. Yeah. Start here. Yeah. And start down here. We give them our direction. We give this our direction. We give this our direction. and we give this our direction. Now, in the case where mu is greater than 0 and the lambda is less than 0, this will be your lambda, this will be your mu. Remember, this is your y-axis, this is your x-axis. They lie on the axis themselves. That's why I write them close to it. Now, with that, since mu is now positive, we will have outgoing direction for mu. We'll have incoming direction for the lambda because lambda is less than 0. And if we follow our baselines, we'll be able to draw or construct our solution curves. Okay. So again, this give it our direction, we'll give it our direction, we'll give our direction, and we'll give our direction. So this is called a saddle. Now, this is how saddles are supposed to look like, and this is how they look like. So whenever you are drawing a system and you have a saddle, and you don't get your diagram to be in this form, then there's something wrong. Our last but not the least is a center. When you have your solution to be a center, you're going to look at two diagrams. You have our x and y axis. For the center, our solution curve, it gets spiral around the origin, which spirals around the origin in a closed curve. And they also have different directions depending on the value of B. Now, in our stable focus, we had A, the value of A to be negative, which is non-zero. And on stable focus, we had the value of A to be positive, which is also non-zero. Now, for center, the value of A is 0. So we have pure imaginary eigenvalues. That means our lambda is equal to plus or minus IB. So if we pick our lambda to be equal to IB, this is what we will get. If we pick our lambda to be equal to minus IB, we'll have this. Now, for B greater than 0, our system will move in this direction, this, and this. And for B less than 0, we'll have this direction. We have this direction. So these are the types of face portraits that we will have for a 2x2 systems. It should be pretty easy to when you get used to it. In the next video, we will take a look at different examples and how to construct their face portraits. See you in the next video.